Welcome to your asynchronous day. We're going to be talking about sections 4.1 and 4.2. Sections 4.1 is about maximum and minimum values. We're going to start with a couple of definitions. So the first is that for an absolute maximum or absolute minimum, and that is an absolute maximum is the value on or value of f on its domain such that f of c is greater than or equal to f of x for all x in D. So that value f of c would be the absolute maximum. And then similarly, the absolute minimum, same idea, except f of c is less than or equal to all the f of x's on the domain. So part 2, it talks about local maxes and mins. So again, a local maximum is a number f of c such that f of c is greater than or equal to f of x, where x is near c. So we're just talking about the local area around c. And then a local minimum, same idea, except f of c is less than or equal to f of x for all x near c. So just to see a little illustration here of what we mean, let's take a look at a picture. So here's an x and y axis, and maybe we have something like so we have three values of interest here. So we have x1 comma f of x1. We have x2 comma f of x2. And we have x3 comma f of x3. So if I look at x1 f of x1, if I look at like this neighborhood, that is the f of x1 is smaller than all the other f of x's in that little neighborhood. So that's like a local minimum. If I look at x2 comma f of x2, that is also a local, well, let's go back to this one. But this is not a global or an absolute minimum, because if I extend this out, look, there's some spots like over here where the f of x's are lower. So it's just local, not global, or absolute is, I guess, what our textbook is using. If I do the same thing here for x2 comma f of x2, so definitely local maximum, but it's not an absolute maximum. So if I extend this all the way out, look, I have arrows at the end here going on forever. So those would be a situation where that's going to keep going, and the f of x's on those arrows would be bigger than that f of x2. And our last one here is x3 f of x3. So again, that's a local minimum. If I make a little box around that neighborhood, it's the lowest point in that box. But if I look, if I extend this out, it's also an absolute minimum, because if I look at the entire graph, that is the lowest point on the entire graph. So again, this should be these terms should be a review. They're something we talk about in Algebra 2 and Trig and Pre-Calc, and maybe even a place or two before that. Our next idea is the extreme value theorem. So The extreme value theorem, oftentimes this gets abbreviated as like EVT, right? We saw the intermediate value theorem in the previous chapter. Here we're seeing the extreme value theorem, and in the next section we'll look at the mean value theorem. But here, again, we're using that EVT as an abbreviation. So it says, if f of x is continuous on the closed interval AB, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d on that closed interval. Okay? Well, let's see what that is really saying, right? So let's draw some pictures to kind of make sure we understand what's going on. So let's say this is A and B. So we have some point. So it's continuous on the closed interval AB. So I have some point here, A comma f of A. And then I have some point here, B comma f of B. And I just kind of arbitrarily place those. If it's continuous on that interval, that means I should be able to connect A and B without picking up my pencil. So maybe if it just looks like that. Well, where's the maximum and minimum going to be on this? Well, there's my min. And there's my max. Critically important that this is a closed interval. If I didn't have that closed interval requirement, I would not necessarily need to have an absolute maximum or absolute minimum. So if those were open circles, those would no longer be absolute maxes and mins, and there would be no absolute max or absolute min. In fact, there would be no even local max or local min on that. Right? But that's not the only way that this situation could have looked. Right? So I have A and B. So again, do this. So here's my A comma f of A. Here's my B comma f of B. And it's continuous, so I can do whatever I want. And look, there's my absolute max. There's my absolute min. Yeah, but Mr. Kulik, what if there's more than one of those? Well, it's fine, right? It's not a big deal. Again, all it says is they exist. Doesn't tell you how many of them there are. So like, here you have 3 absolute maxes and 3 absolute mins. That's fine. Okay, Mr. Kulik, but what if it's just like a constant function, right? All right, so what? So what's that say? Is every point on that segment would be an absolute minimum and also an absolute maximum. Because any point on there, its y-coordinate is equal to every other y-coordinate. So it satisfies the requirements of an absolute minimum and also satisfies the requirements for an absolute maximum. So that's all it's really saying, is that if you have some closed interval and a continuous function on that interval, somewhere in there you got to get at least one absolute minimum and at least one absolute maximum. And that's it. That's all it's really saying. Again, if you didn't have to have the continuity or you didn't have to have the closed, then you don't have to have maxes and mins. So if I have closed interval but I don't have continuity, I could have something like this, where there's no absolute max or min because I have arrows pointing up and I have an arrow pointing down, so there would be no absolute max and min. That's if I didn't have continuity. The other part that I have to have on here is the closed interval. So if it's not closed, I'm just going to use the same example I used before. If I have this, here there's, again, no absolute min, because while you're approaching the point a comma f of a, you never actually get to that point, and you can always find something that's just a little bit smaller, a little bit closer to f of a. So there's no absolute minimum. And similarly, there's no absolute maximum. Again, you can go really, really close as you want to b comma f of b, but you can never get to f of b. But anything you can find, I can give you something that's a little bit closer. You know, if this is the point like, 1, 3, I can have like 0.9, 2.9, and 0.99, 2.99, and 0.999, 2.999, and you just keep getting closer and closer and closer and closer, finding bigger and bigger and bigger values of f of x. But anytime you find a bigger value of f of x, you can just like add another digit to the end of it, and you have a bigger value of f of x, and you haven't gotten to f of b there. So again, no maxes and no mins. It's certainly possible to, or no absolute max and no absolute min. It's certainly possible to draw that if you don't have the closed interval requirement. All right. Next up is called Fermat's theorem. So if f has a local minimum or local maximum at C, and if f prime of C exists, then f prime of C is equal to 0. So this we have to be a little bit careful about because it's easy to treat this as something stronger than it is. So let's show you that the converse isn't true, that if just because I have a place where the derivative is 0 doesn't mean that we're going to have a maximum, a local maximum or local minimum there. So let's say we have f of x is equal to x cubed. So f prime of x is equal to 3x squared. Well, and I notice that f prime of 0 is equal to 0, but 0, 0 is not a local max or local min on the function f of x, right? If you graphed y equals x cubed, you get something like this. Notice that that's not a local min or a local max. If I look at the neighborhood surrounding that, no matter how tightly you get that box, the value on the far right is still going to be bigger than 0, 0. So it can't be a local maximum. And the value on the right of the box, or the left of the box, will still be smaller than 0, 0. So it can't be a local minimum. So just because the derivative is equal to 0 someplace doesn't guarantee that it's a maximum or minimum. However, if you have a maximum or minimum, the derivative there is either going to not exist or be equal to 0. The other place where we have to be careful is a lot of times we forget about the does not exist possibility. So you can still have local maxes and local mins, but the derivative might not exist there. So the easy canonical example is the graph of the absolute value. So remember, if I look at the graph of the absolute value of x, you get that kind of V-shaped. So I can see really quickly that 0, 0 is a local minimum. That's the lowest point on the graph. 0, or f of 0 if you'd prefer to think about it that way, is smaller than or equal to every other point on the graph. So in fact, it's also an absolute minimum, but that's fine. Absolute minimums are also local minimums. But the converse is not also true, right? Local minimums are not always absolute minimums. But I know that the derivative here does not exist, right? Because the limit as x approaches 0 from the left of f of x minus f of 0 divided by x is -1, and the limit as x approaches 0 from the right of f of x minus f of 0 over x is equal to +1. And since the left-hand limit and the right-hand limit disagree, so the limit as x approaches 0 of f of x minus f of 0 over x does not exist, right? This was a, oops-a-daisy. We did this way back in chapter 2. That's going back to the limit definition of a derivative. Oh no! Yeah, you thought you would get away with not seeing that again, and here it is creeping back up. But that's the point of this, is to remind you that just because we have a function where the derivative is never equal to 0 doesn't mean that we won't have a maximum or minimum. We have to remember there's still that places where the derivative fails to exist possibility there to handle. The next piece is the critical number. So this is just a definition. So we say a critical number of a function, f is a number c in the domain of f, such that either f prime of c is equal to 0 or f prime of c does not exist. This will essentially become our candidates for local minimums and local maximums. So let's do a quick example here. So let's say we have the function x to the 3/5 times 4 minus x. And we're looking for the critical values. I abbreviate that as CV. So there's a couple of, what we need to do is we need to look at f prime. And I guess before we do that, let's just state the domain for f of x. So the domain for f of x is the product of two functions, right? The yellow function is a linear function, just looks like y equals mx plus b. The domain for a linear function is all real numbers. Okay? X to the 3/5 is the same thing as the 5th root of x to the 3rd. I know that the domain for any odd root is all real numbers. And I know the domain for any polynomial like x to the 3rd is also all real numbers. So the domain for this product of two functions, each of which have the domain of all real numbers, is just going to be all real numbers. So now let's look at the derivative then. To do that, I might first want to do some algebra to avoid having to do the product property. I could distribute that through. And then we can do the, and then we can take our derivative. That might make life a little bit easier, but the product property wouldn't have been so bad either. So when I do that, I get 4 times 3/5 x to the negative 2/5 minus 8/5 times x to the negative 3/5. I think it would behoove us in this situation to write this with positive exponents. So what we have to do now is we have to consider the domain for this function, because we're interested in where the derivative doesn't exist. So any place where this expression, 12 over 5 x to the 2/5 minus 8 over 5 x to the 3/5 doesn't, or is undefined, would be places where the derivative does not exist. Here I'm interested in two things. I have a radical function, which I know can be undefined, and then I have a quotient or rational function, which I know can have undefined pieces. Now the radical piece is easy because they're both odd roots, because they're 2/5 and 3/5. That's the 5th root of x squared and the 5th root of x cubed, respectively. Again, we said before, odd roots have a domain of all real numbers, so that part I'm fine with, no big deal there. The rational function, though, I know I have to worry about. I know a rational function is undefined whenever the denominator is 0. Well, I can tell by inspection that this function, or each fraction, will have a 0 denominator when x is equal to 0, right? 0 to the 2/5 is 0. Times 5 is 0, 12 over 0 is undefined. Great. And then likewise, 0 to the 3/5 is 0, 0 times 5 is 0, and 8 over 0 is also undefined. So my domain here is just going to be all real numbers except for 0. So that's one thing I have to check for. So I know that f prime of 0 does not exist. So that's one critical value. The other place I have to find is looking at where the derivative is equal to 0. So I think I might go back to this step. It'll probably be a little bit easier to deal with there. Without those, well, I guess it doesn't really matter. Let's keep them in the denominator, I suppose. That's probably what you would have done anyways. The algebra is not much worse. In fact, if you use the product property here, this algebra would have been better, but that's okay. So what I'm going to do is factor this now. So what do I get if, or to solve this to equal to 0, I need it in a factored form. Let's put it that way. Probably the easiest thing to do would be to factor out 5x, or 1 over, well, I'd say, actually, let me retract that. We'll take out 4/5 x to the 2/5. So that's going to become 3 minus, and then when I divide 8 by 4, I get 2. The 5 goes out of there, and I'll be dividing x to the 3/5 by x to the 2/5. So when I divide exponentials, I subtract the exponents. And then I can take each one of these two factors and set them equal to 0. And solve them each independently. So this first one, 4/5 or 4 over 5x to the 2/5 equals 0. Well, I can see right away that this has no solution to it. If you multiply both sides by 2x to the 2/5 to get the x out of the denominator, you just have 0 equals 4/5. So that's clearly a nonsense solution. If we go over here, we'll multiply both sides by x to the 1/5 to get that x out of the denominator. And then I'll add 2 to both sides, divide by 3, and then raise that to the 5th power. Okay, so Mr. Kulik made a boo-boo here. You probably caught it. I was like, why isn't this working out? So I'm going to erase this stuff down here because that's all boo-booed. But here's the problem. When I did my derivative here, when I subtracted 1, this should be plus 3/5. Oh no! Yeah, big boo-boo there. It doesn't change too much initially because we still have the same problem. My rational function can give a 0 denominator, can't have a 0 denominator, so I have still the same critical value for x cannot equal 0. That's fine. But now I have a little bit different when we're solving. So I'm going to erase all this stuff that I was solving because it's not quite right. Okay. So this is what I'm solving. So to do this, what I'm going to do is make a common denominator. So I'll just multiply the top and bottom by x to the 2/5 here. So I'd have 12 minus 8x over 5x to the 2/5. And I know a fraction can be equal to 0 when the numerator is equal to 0. So all I really need to do is solve 12 minus 8x equal to 0. That's what I was expecting. So subtract 12, divide by 8, and reduce is 3 over 2. So that's my second critical value. Sheepers creepers. Okay, my apologies for making that little goofy goofer there. Next little theorem, or this is probably more like a lemma. It's a minor theorem. That's what a lemma is. If f has a local maximum or local minimum at C, then C is a critical number for f. Okay, so again, to find a local max or min, we can just find the critical numbers and then check those out. And that leads us to this last idea in section 4.1 called the closed interval method to find the absolute maximum and minimum values of a continuous function f on a closed interval a, b. We want to first start by finding the critical values of f at the critical numbers of f in the open interval a, b. And then we're going to find the value of f at the endpoints of the interval. And then we want to take the largest of the values from step 1 and 2 and the smallest of the values from step 1 and 2, and those will be our absolute maximum and absolute minimum respectively. So let's do a couple of examples. So let's say we want to find the absolute maximum and absolute minimum, where we have this function f of x, and we're on the closed interval (-1/2 is less than or equal to x is less than or equal to 4. Notice that I wrote this as a set of inequalities rather than an interval. How do I know that this is a closed interval? It's because they're both or equal to. If I didn't have the or equal to, I could not use this method. All right. So starts wanting me to find the critical numbers. So to do that, I'm going to find the derivative. And then I'm going to set that derivative equal to 0. I guess while I'm doing this, I'm going to observe that the domain for this is all real numbers because it's a polynomial. When I take the derivative, the domain the derivative's a polynomial also, so for the domain is all real numbers there as well. So I don't have any places where the derivative is undefined, which is swell. So the derivative for f is all real numbers, and the derivative for the domain for f is all real numbers, and the domain for the derivative of f is all real numbers. So that's nice. So I'm just left to solve this polynomial then. I know this polynomial is quadratic and it's easy to factor, so I'm going to solve it by factoring. You could use the quadratic formula here, but like, why? And hopefully you can see now that it's factored by inspection that the solutions are going to be x equals 0 and x equals 2. So those are my critical values. So that's like my step 1. And then I have to evaluate, those. So I'm going to do f of 0, f of 2. And then in step 2, I also want to check the critical value at the endpoints, f of -1/2 and f of 4. So I'm just going to plug those back into f here. And I've done this already, so I'm just going to write down the numbers here for us. So f of 0 is 1, f of 2 was -3, f of -1/2 is 1/8, and then f of 4 is 17. So this is my absolute maximum, and this is my absolute minimum. Now keep in mind, when I say that, that's the absolute maximum and absolute minimum on the interval from -1/2 to 4. That does not mean over the domain of the function. That means those are the absolute minimum and absolute maximum on that closed interval, not over the domain. Hopefully you can see by looking at this, there is no absolute maximum and absolute minimum for that f of x because it's an odd polynomial. So I know the the left end of the graph is pointing down and the right end of the graph is pointing up. So there would be no absolute minimum and absolute maximum over the entire domain. There is, however, absolute mins and absolute maxes over some closed sub-interval of that domain. So let's do one more, and that'll be all for today. Well, for this section anyways. So let's say our function is f of x equals x minus 2 sine x. and we're looking at the domain, or the closed interval, I shouldn't say domain, the closed interval 0 to 2 pi. Okay, so let's go ahead and find the absolute minimums and absolute maximums. So I'm going to start by taking, well, we should probably talk about the domain here. X is a polynomial, its domain is all real numbers. 2 sine x is a trigonometric function. I should remember from trigonometry that the domain for sine and cosine are both all real numbers. So this function is just a difference of two functions who have domains all real numbers, so its domain should be all real numbers as well. We'll take the derivative then. That's going to be 1 minus 2 cosine x. Again, 1 is a constant function, so its domain is all real numbers. And then cosine, again from trigonometry, remember its domain is all real numbers, so the difference of two functions whose domain is all real numbers should still be all real numbers. So now I care about this. So to find the critical values then, I don't have anything where the domain is undefined. So I'm just going to solve here. So if I subtract 1 from both sides and then divide by -2, I have cosine, or 1/2 is equal to cosine x. I'll do the cosine inverse to both sides. And I have that x is equal to cosine inverse of 1/2. Hopefully when you look at this, you recognize that 1/2 is a unit circle value. So if I go back to my unit circle and think about where cosine is positive, that happens in quadrants 1 and quadrants 4. Cosine is the x-coordinate. Hopefully you'll recognize that the matching y-coordinate there would be √3/2 and -√3/2 respectively in quadrants 1 and 4. This hopefully we recognize as pi/3, and then this one as 5π/3. Those are things that you should have memorized, or at least be able to draw a picture and be able to reason your way through. Worst case scenario, if it's a calculator problem, you could do cosine inverse of 1/2 in degree mode, which comes out to be 60 degrees, and then you could convert that into radians. But this is one that you should be able to recognize. We did a lot of practice with this last year. So those are my critical values. Okay, so I definitely need to do f of pi/3. Well, that's actually, that actually work. And then f of 5π/3. And then we also need to do the endpoints, so f of 0 and f of 2π. So again, remember, we're plugging into f of x here. So we have pi/3 minus 2, and then sine of pi/3 we have right here, √3/2. So I have pi/3 minus √3. We do the same thing, so 5π/3 minus 2 times, and that's negative √3/2. So that's going to be pi/3 plus √3. So I know immediately now that this one can't be a maximum, because clearly this one is bigger since I'm adding √3 instead of subtracting it. 0 minus 2. What's sine of 0? Right, 0 degrees is here. That's the point 1, 0. Ooh, boy, is it. So sine of 0 is 0. And if we do the same thing here, sine of 2 pi is at the same spot. So 2 pi minus 0 is just 2 pi. Okay. So my question is, I have to see which one of these two is bigger and which one of these two is bigger. Well, let's think about it for a moment. I imagine if I didn't have a calculator here. So square root 3 is about like 1.6-ish. Pi over 3 is like going to be a little bit more than 1. So 1 minus 1.6 is going to be a negative number. So that one should be our absolute minimum. That one should be negative. So I know that's smaller than 0. And then let's look at the other one. So, ooh, my boysies. Look at this, guys. Was 5 pi over 3, so that should be 5 pi over 3 plus 3. 5 pi over 3 is going to be, what's that got to be, about 5-ish, right? 6 pi over 3 is like 6.2-ish. And then if we subtract 1, we're going to be 5.2-ish. And if we add 1.6 to that, that's going to be like 6.8-ish, which is bigger than 6.2-ish. So this is my absolute maximum here. Ideally, you could also just type that crap into your calculator and see which one is the biggest and smallest. But again, I like to kind of talk through some of these things in case you run into something like this that fell on a no calculator portion. How would you even go about doing that? And it's just about like just trying to make an estimate, right? Pi over 3 is like 3.14 divided by 3. What's that? A little bigger than 1. So let's just use 1, you know, and just kind of go about doing that kind of thing. That's it for this section. It's pretty light. So 3 through 13 odds, 35, 37, 40 to 43, 49, 51, 53 through 55, 57 to 62, 66, 70, 74, 75, and 78.